Good morning, good afternoon, and good evening. Welcome to today's webinar in the webinar series brought to you by the ITU AI and Machine Learning 5G Challenge. My name is Thomas Pascal from the ITU, and it is my privilege to introduce today's webinar. The AI and Machine Learning in 5G Challenge is organized by the United Nations Agency, ITU, which is the United Nations Agency for ICTs. And this challenge is kindly sponsored by Xilinx. We are grateful for their sponsorship. The aim of the challenge is to create a community that will solve network-related problems using AI and machine learning. Today's webinar is going to be given by Jiashen Xiong. Jiashen received the master's degree from the University of Chinese Academy of Sciences in 2014. He has several years of algorithm development experience in computer vision and machine learning. Currently, he's working in the China Unicom Network AI Center, and he's leading the team in research and development of network intelligence operation and maintenance algorithm. These include KPI anomaly detection, energy saving prediction of base station, log anomaly detection, etc. Today's talk will introduce the problem statement number 5, which is anomaly detection based on log analysis. In this challenge, there will be an exploration of anomaly detection that is based on the log that will be presented in this webinar. The log messages are collected from real service. So the data set that you are going to receive is real data set from 5G network. Participants are expected to use the AI techniques to analyze the log files of the failed run to support operators' quick root cause analysis. So at this time, I would like to welcome Jiashen. Good afternoon, Jiashen. Welcome to the ITU AI and Machine Learning 5G Challenge webinar series.
Okay, hello everyone. My name is Jiashen. Today I'm very glad to join this webinar. And here is my email address. You are very welcome to contact me if you have any questions regarding to this challenge. And this speech will be about 4 parts. Firstly, we'll introduce anomaly detection in log files. Then I'll demonstrate the framework and methodology of log file anomaly detection. Lastly, I'll introduce our challenge statement. Okay, let's go to the first part, introduction. Logs, as we know, they record system runtime information. And it is unstructured data with various formats and massive size. Traditionally, operators manually check system logs or write rules to detect anomalies based on their domain knowledge. And in addition to that, they may use keywords search or regular expression match. For example, fail, exception. However, such anomaly detection that relies heavily on manual inspection of logs have become inadequate for 5G network systems due to the following reasons. Firstly, 5G network system behavior is too complex to comprehend by each single operator. An operator might have only incomplete understanding of the overall system behaviors, thus making it a great challenge to identify issues from huge logs. And secondly, the 5G network system generates tons of logs. That is, each data center runs into 100 million lines per day. The huge volume of such logs makes it extremely difficult to manually discover the key information from the noise data for anomaly detection. As a result, automated log analysis methods for anomaly detection are highly in demand. And here is an example of the logs. They are unstructured data. Then, now you may ask me how to realize anomaly detection in logs. I'll show you the framework of this. The figure shows the overall framework. It involves 4 parts: log collection, log parsing, feature extraction, and anomaly detection. Let's say log collection. Large-scale systems routinely generate logs to record system status and runtime information. each comprising a timestamp and a log message indicating what has happened. For this example, it depicts 8 log lines from HDFS logs. Then the second step is log passing. Logs are unstructured. The purpose of log passing is to extract a group of event template to make it structured. In this example, the fourth log message is passed as event2, this line, with an event template received block star of size star from star. After passing logs into separate events, we need to further encode them into numerical feature vectors so that machine learning models can be applied. To do so, we first slice the raw logs into a set of log sequence by using different grouping techniques, including fixed windows, sliding windows, and session windows. Then for each log sequence, we generate a feature vector, such as this, a feature vector, which represents the occurrence number of each event. Our feature vectors can form a feature matrix, event count matrix. And finally, the feature matrix can be fed to machine learning models for training and thus generate a model for anomaly detection. The model can be used to identify whether or not a new incoming log sequence is an anomaly. This is a framework of this. And let's go to the third part, methodology. Constant paths are predefined in source codes by developers, and the variable paths are often generated dynamically. For example, the port number, IP address, like here. The purpose of log parsing is to separate constant paths from variable paths and form a well-established log event, which is, in this example, connection from star closed. This is a template. I will introduce a log passing method. The first is drain. Drain is a fixed depth tree based online log passing method. When new raw log message arrives, drain will preprocess it by simple regular expressions based on domain knowledge. Then we'll search a log group, which is leaf nodes of the tree, by following a specially designed rules encoded in the internal nodes of the tree. If a suitable log group is found, the log message will be matched with log event stored in that log group. Otherwise, a new log group will be created based on the log message. Compared to drain, this is a FT tree. This is another log passing method. And compared to drain, FT tree does not rely on any domain knowledge. It is an incrementally trainable technique for log event extraction. It is an extended prefix tree structure for encoding message templates. The basic idea behind FT tree is that a log message subtype is usually the longest combination of words with high frequencies, and hence extracting a template is equivalent to identifying such longest combination of frequent words from log messages. And FT tree here lists the main steps of FT tree. The first step is to arrange each line of log words in descending order according to log word frequency. As you can see, it is here. And the second step is insert descending word sequence into a tree structure, just like this. And the third step is prune the tree, remove the node which has too many children, as you can see here. And FT tree is support incremental template learning. Okay, then let's go to feature extraction. I will show you some methods here. The main purpose of feature extraction is to extract valuable features from log events that could be fed into anomaly detection methods. The input of feature extraction is log events generated in log parsing step, and the output is an event count matrix, just like this. In order to extract features, we firstly need to separate log data into various groups, where each group represents a log sequence. To do so, windowing is applied to divide a log dataset into finite chunks. We can use 3 different types of windows: fixed windows, sliding windows, and session windows. Let's go to the first one, fixed windows. Both fixed windows and sliding windows are based on timestamp, which records the occurrence time of each log. Each fixed window has its size, which means the time span or time duration, as shown in this figure. The window size is delta t, which is a constant value, such as 1 hour or 1 day. Thus, the number of fixed windows depends on the predefined window size. Logs that happened in the same window are regarded as a log sequence. And then let's see sliding windows. Different from fixed windows, sliding windows consist of 2 attributes: window size and step size. For example, hourly windows sliding every 5 minutes. In general, step size is smaller than window size, therefore causing the overlap of different windows. This figure shows that window size is delta t, while the step size is a forwarding distance. The number of sliding windows is often larger than fixed windows. It depends on both window size and the step size. Logs that occurred in the same sliding window are also grouped as log sequence. Those logs may duplicate in multiple sliding windows due to the overlap. The last one is session windows. And compared with above 2 windowing types, session windows are based on identifiers instead of the timestamp. Identifiers are utilized to mark different execution paths in some log data. For instance, HDFS logs with block ID record the allocation, writing, replication, deletion of certain block. Thus, we can group logs according to the identifiers, where each session window has a unique identifier. After constructing the log sequence with window techniques, an event count matrix is generated. In each log sequence, we count the occurrence number of each log event to form the event count vector. For example, as you can see here, if the event count vector is this, 1, 0, 2, 0, 1, 0, 1, 1, 0, 1, it means that event 1 occurred once in log sequence, and event 3 occurred twice in the log sequence, event 5 occurred once in the log sequence, and so on. Finally, plenty of event count vectors are constructed to be an event count matrix. Here. After feature extraction, we'll go to anomaly detection. This is the last step of the framework. And anomaly detection, we can use supervised learning or unsupervised learning to solve this problem. But in real world, unsupervised learning is more applicable. Due to the lack of labels, we do not have enough labels to train supervised learning models. And so here, you can directly feed the event count matrix to the machine learning models. The common approaches include log clustering, PCA, and so on. And there's another interesting method I would like to talk about. The first step is to convert the event counts to chi-squared states. In this step, you can also try the methods like Bayesian likelihood, TF-IDF Chi2, and autoencoder, and so on. And next, we can sum up the chi-squared states. And lastly, we we can use 3 sigma to detect outliers in time sequence. You can also try other time series models or even static threshold. And we assume the chi-squared states is normal distribution because the log size is big enough. Okay, I'll talk about the last part, challenge statement. To get close to real-world production environment, the datasets we provided come from our 5G systems and are unlabeled. It includes transets and test sets of message logs and sysmonitor logs. The transets record the logs of system in functioning, while the test sets contain a few records of system anomalies, like server power down, insufficient memory, and so on. This challenge evaluated by F1 score and code efficiency. So both the code and the answer file should be submitted. We provide a concatenated answer file for submission, where the order is message log first and the sysmonitor log next. The time slice is calculated from the date time in test sets. They are converted to timestamp, then divided by 300 and rounded up to the integer. Last, I talk about a trick. The trick of this task is that logs contain keywords like failed, error, one, that do not necessarily represent system anomalies. That's all. Thank you for listening.
Thank you so much, Cheshin, for this quick introduction to problem statement number 1. Right now, I would like to go into the Q&A session. So maybe I would like to invite my colleague, Vishnu. Hi, Vishnu. Good afternoon.
Hi, Thomas. Hi, Jason.
Hi.
Okay, I want to start with one question about test set. Is the test set available for participant? This test set log files with anomalies, is that available for participants, or is that only for evaluation?
Yes, the test set is available on the platform.
Okay, and when you so how do you evaluate these submissions? So do you have another test set to evaluate, or how do you evaluate these submissions?
Okay, the test set on the platform is unlabeled. It's only some logs and it's logs that you can see normally. It's unlabeled. It's text, and the label of each and the label of the test sets is and we have the label of the test sets. And when the participants uploaded their results, we can compare their labels with our labels, and we can compute the F1 score out. Yeah.
Thank you. Why the training set without anomalies? Why the train set has no anomalies?
Okay. First, the log in the real world, it's very difficult to give label to the train data, because the train data is very large. It may contain 1 million or more lines of logs, and we cannot manually give a label to every line. So in the real world log anomaly detection, the algorithms often we often use unsupervised learning to solve this problem. So there is no label. Yes.
Mm-hmm. So if I understand you correctly, the train set have no labels, but they are collected from real data, a real network, and it may have anomalies, it may not have anomalies. It's just real data. That's what you mean, right?
There is no anomalies in the train data because we need to extract some patterns, some normal patterns from the train data, and then we can use the correct pattern to compare with the test sets, because there are anomalies in test sets. After we train our model on the train sets, we can use it to detect anomalies in the test sets. So there are no anomalies in the train set.
Okay, okay, understood. Thank you. And the participant, what does she submit? Do you have a page where do you have a description what the participant has to submit to you? Is that there it is, a source code and a CSV file. What does a CSV file contain?
Okay, I have upload the CSV file to the platform, and the format of the result file is contained in that. It contains three columns, and participants can download it from the platform. They will see, and they can upload their result according to that.
Okay, thank you. There is a question, constant part of the log is in constant part of a log the label of the log. So what is a constant part of the log? I can't find. Didier is asking, is in constant part of the log label of the log. Where is constant part of the log? So you have a yes. Thank you. Yeah, please explain.
Okay, constant part is in this example. Constant part words like connection, from, and closed, and the variable part are the IP address. Yeah, because in our codes, the developers they will write these words like connection, from, and closed. They'll be right in the source code, but the IP address will dynamically changed when we run the code.
Understood. Thank you. Yeah, I think the constant part is the patterns. I think they are fixed patterns and they can be used to train the model maybe. Okay. Could there potentially be anomalies that are not detected by your teams in train sets and test sets? So the question is, your team has the solution, your team has the answer which you are checking, but are there anomalies which your team has not found? It is they are hidden from your team also. So I think that's the question, because these are logs from real network. So I think the question is, have you missed any anomaly, Jianfeng, from your own logs?
There may be a few exceptions, a few anomalies we may not found it out. We collected the data from the real world, and we communicate with the the operators, they told me, they told us that there are about 4 things that there are about 4 things that the anomalies will occur, like server power down and insufficient memory. These are the main causes of the anomalies. And the rest of the log, I check it out. I check it, but in my knowledge, I did not see another anomaly. So there is maybe some anomalies will maybe not discovered, but it's very few.
Thank you.
Yeah.
Thank you, Jenshong. We trust you with your logs. Thank you so much. There is another question about the trick node. So if you go to the trick in the last slide, I think there you had the trick. Could you
Sorry.
go to the last slide? There is a trick node in the last slide. Yeah. So trick says the logs contain keywords like blah 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 and do not represent system anomalies. Yes. So yeah, I think this was my question also, that these are local errors but may not be system anomalies. Is that what you mean? So we participant look for system anomaly, not local failures which are error warning failed, etc. What is this trick? Can you explain this trick? Why you say system anomaly here?
Because developers, we develop our codes. We may add some message like some logs to show what is the system status now. But the words field error 1. In the real world, as we can see, I check the logs. I check a lot of logs, and I talk with the operators. They told me that if a log, even there are a lot of failed and error and 1 in the logs, then that did not mean that the equipment is bad, is broken. It may the facility, the equipment may still function well. So so the labels, the anomalies, we label it according to the real business. Yeah, not according to the keywords, because even these keywords occurred, the equipment still function well. Maybe.
Understood. Yeah, I understand it as that you could some of these occurrences of the keyword may not mean catastrophic failures or system anomalies. The system is still functioning even though such keywords appear. So you have to look at the context, I guess, to find out whether system anomaly happened. Can I ask, actually, that's a good question, Tariq. Can I ask what kind of system anomalies? What kind of system anomalies, please, Jenshong? Can you explain what kind of system anomalies?
And the anomalies in our test sets, there are 2 kinds of it. First is like server power down, and then insufficient memory. These are main 2 kinds of it. Yeah.
Thank you. So yeah, I think that is clear now. So there is Filippo asking, is it time occurrence of events going to be included in training test data sets? Yeah. So I see time slice here, time slice, and you mentioned the sliding window, sliding time window, or session window. What is used in these logs? Which of, is it fixed window, sliding window, or session window? What is used in these logs, and how is the time represented in these logs?
These windows are used to extract features from the log text. They are used to generate the feature matrix, this event count matrix, just like here. For example, we can use fixed window. The fixed window can split the logs into chunks, a lot of chunks, and each time duration is delta t, and it contains maybe many lines of logs, and it's all called a log sequence. And the log sequence can be converted into an event count vector, just like here. It means it contains many lines of logs, and the event count vector, just like here, it means event 1 occurred once in the log sequence, and event 3 occurred twice, just like so. And then every log sequence can consist of this.
Okay, thank you. So the session count. So if you go back to the last slide, Johnson, in your last slide, there is a session number or session count. Can you please explain what is that in the last slide, please? Time slice. Yeah. What is that time slice?
Okay, the time slice is generated according to the test sets, the timestamp in the test sets. The algorithm of generating it is described in the read file. Participants can read it. They will generate it just like this. It's very simple calculation. Yeah.
Okay, thank you. There is another questions from Tariq is asking, since we will not be able to see an anomaly sample, does your test set include anomalies based on broken correlation between events, or just based on frequency of certain events? Based on broken correlation or between events, or just based on frequency of certain events? So I guess the question is, how do participants map the patterns to the patterns and events in the log to the anomaly? Is there a correlation that you need to look for, correlation, or is it frequency of certain events? Can you explain, Jianshong?
Participants can detect anomalies according to frequency. There may no clear correlation between from the logs. They can detect the anomalies from according to frequency. Yeah.
What about the two separated events? So you have event 1 and event 2. Do you need to correlate between event 1 and event 2? Do you have to look at the separation or different events and correlate? I think that's the question.
Yeah. Participants can the log anomaly detection, they can detect anomalies according to event correlation. But in this challenge, they can detect anomalies just according to frequency. There may in the training dataset some anomaly log may not appear, but in the test sets anomaly logs will appear. So they can detect anomalies according to frequency because there may no anomalies in transit.
Yeah. For example, is there a sequence of events like event A always comes before event B, and is there a sequence of events that one participant look for, and if that sequence is not correct in the test data set, then do we classify it as a failure, as an anomaly?
The approach you talk about is a solution to LAD to log anomaly detection, but as I say, it's not a solution. Maybe it's not a solution in our challenge. Yeah.
Got it. Understood. Thank you.
And participants can try it. Yeah.
Thank you. There is what type of logs are these? So these are you told that low memory out of memory, and power. I think you mentioned shutdown. These are the two different types. Yeah. These are two main anomalies that we look for. These are core network, or is this a transport, or is it a radio access? Are you okay to tell what type of logs these are?
Okay. There are main two anomalies in these logs. Just like I say, server power down and insufficient memory. And these two anomalies, they appear in both test sets. The test sets it contains two logs. One is message, and another is seismometer. And server power down and the insufficient memory, they all contained in the logs.
Okay. Is the testing step using the same features than the training step, or testing step new features can be discovered? So features are the same from training to testing set, or is there a new feature in the testing set? As the question.
Yes, new feature will appear in the test sets because there are some anomaly logs in the test set, and there is no anomaly in train set. So some new feature will appear in the test sets, and the participants will need to detect the anomalies according to these new features.
Okay, thank you. I want to ask Jianshong, is there any baseline that you're looking for? So in your evaluation of your logs, is there any baseline score that that is that you have seen? Is there a baseline test that you have done? Is there a baseline score that accuracy recall F1 score that you have from your lab? Is there something like that?
Okay, the baseline of this challenge is about the F1 score is about 1.65.
Okay.
0.65. Yeah.
Okay. Okay. Yes, I think that's all the questions that we had. The so I think the submission process is quite clear. You explained it already, and the data is clear as well. I think the problem statement also is very nice. You have data from real network. So I think this is a really good, and it is unstructured data. So it's even more good. I think this is a very nice problem statement, and you have patiently answered all the questions, Chenshong. So thank you so much for answering all the questions, and we will come back to you if there are any more questions. Thomas is here. Thank you, Chenshong, for answering all the questions. Over to you, Thomas.
Excuse me. Yeah. I want to share a problem, to share a trick. And in this challenge, participants may need to use sliding window to solve this problem. Yeah. Because in our answer, the participants should submit their result every 5 minutes. Every 5 minutes, give a label. Yeah, and it is described in the data set.
Okay. Yeah. Thank you, Jenshong. Yeah, that makes sense. Every 5 minutes. All right.
Yeah.
We note
Every
that.
5 minutes.
Yes. Thank you. Is that in your website? Is it explained in your problem statement also?
Yeah.
Okay. Yeah. Thank you.
Thank you so much, Vishnu, and thank you, Jashin, for the Q&A. We appreciate. I would like to make a few announcements. First is that this problem statement number 5, you can find it on the challenge web portal. Just go on the problem statement and look for problem statement number 5. You'll find it. You register, you create your team. The data set is available, or the data set that was described by Jashin here is already available, so you can download and start working on your solutions. Some teams have already started working on their solutions, and if you have your results, you can already start your submission of the results. So we are really looking forward to more participants to join in this problem statement. I would also like to make an announcement that the challenge registration is open. We opened the challenge registration, so you can register. Information is available in the challenge website as well as on the problem statement portal. At this point in time, I would like to thank everyone for joining, and I would like to wish you have a very good day. See you in next webinar. Thank you. Bye-bye.